Good day, guys. Our topic is statically indeterminate bodies. So, there are certain combinations of statically loaded members in which the equations of static equilibrium are not sufficient for a solution. Such cases are called statically indeterminate and require the use of additional relations which depend upon the elastic deformation of the members. So, it's a combination of static equilibrium and elastic deformation equation. Okay, to explain, let us have some problems. This is problem number 1. The short concrete post is reinforced actually with 6 symmetrically placed steel bars, each 600 millimeters squared in area. If the applied load is 600 kilonewtons, compute the stress developed in each material. Use modulus of elasticity of steel equivalent to 200 gigapascal and the modulus of elasticity of concrete equivalent to 14 gigapascal. So the figure is shown below. Now the solution is that first we have a given elasticity of concrete equivalent to 14 gigapascal, the elasticity of steel equivalent to 200 gigapascal, and the force equivalent to 1000 kilonewtons. So if we're going to apply the summation of forces vertical, which is your static equilibrium equation, you know that the force of the steel plus the force of the concrete is equivalent to 1000 kilonewtons. So the upward forces are the one reacting to the downward forces, which is equivalent to the load of 1000 kilonewtons. So when that load is applied, your concrete is going to deform, so with your steel, and they are both equal because they are it's a column, it's one solid material. And you know that the deformation of concrete is equivalent to the stress of concrete multiplied by the length of concrete divided by the elasticity of concrete, which is equal to the deformation of your steel, which is stress of the steel, length of the steel divided by the modulus of elasticity of steel. So since the length of the steel and length of concrete are equal, they will both cancel, and you are left with the deformation of the steel all over, no, stress of the concrete all over the modulus of elasticity of concrete, which is equivalent to stress of the steel divided by the modulus of elasticity of steel. And substituting their elasticities, you come up with stress of steel equivalent to 14.29 the stress of concrete. This equation, stress of steel equivalent to 14.29 the stress of concrete, is going to be used in our previous problems. Okay, so therefore the stress of the steel is equivalent to force of the steel divided by the area of the steel. Simplifying, you have the force of the steel equivalent to the stress of the steel multiplied by the area of the steel. We also know that the stress of concrete is the force of the concrete divided by the area of the concrete, wherein the force of the concrete is the stress of the concrete multiplied by the area of the concrete. So substituting in your equilibrium equation, you have now stress of concrete multiplied by the area of the concrete plus the stress of the steel multiplied by the area of the steel is equivalent to 1000 kilonewtons. So the stress of concrete multiplied by the area of the concrete, wherein the area of the concrete is 300 times 300, so 300 squared minus 6 times 600, we are deducting the area of the steel, that is the force of the concrete, plus the force of the steel, which is 14.29 the stress of the concrete, because that is the stress computed previously from the comparison, the calculation of stresses equivalent to 14.29 the stress of the concrete. So that was previously solved for 14.29 times the stress of the concrete times 6 times 600. So 6 times 600 is the area of the steel. So simplifying, you are left with the stress of the concrete equivalent to 7.25. So that equation is equivalent to 1000. So you are left with the stress of the concrete equivalent to 7.25. So therefore, the stress of the steel is equivalent to 14.29 times 7.25, which gives you the stress of the steel equivalent to 103.67 megapascal. Let's go to number 2. We have to consider the figure in problem the figure in problem 1. Assuming that the allowable stresses to be the stress of steel equivalent to 120 megapascal and the stress of the concrete as 6 megapascal. These are the allowable stresses of your steel and concrete. We want to compute the maximum safe axial load P which may be applied. So this one we are going to now compute the force P. In problem number 1, we were solving for the stress. Here the stresses are given and we want to solve for P. So it's a different problem compared to number 1, and the solution is that we have a given we have the given stresses of 120 megapascal for steel and the stress equivalent to 6 megapascal for concrete, and these are the allowable stresses for each material acting independently. Okay, so if you're going to take summation of forces vertical equivalent to 0, the force of concrete plus the force of the steel is equivalent to 400 is equivalent to P, which is summation of forces vertical in your equilibrium equation. Again, the deformation of concrete is equivalent to your deformation of steel. That gives us the stress of the concrete times the length of the concrete divided by the elasticity of concrete is equivalent to the stress of the steel times length of the steel divided by the elasticity of the steel. And the length and of the concrete and the steel will cancel out. That gives you an equation which is stress of the steel equivalent to 14.29 the stress of concrete. That was previously discussed in problem number 1. Okay, so with the relationship of the stress equivalent of the steel equivalent to 14.29 the stress of the concrete, that will happen at the same time. However, if we allow the stress of the steel to reach a stress of 120 megapascal, what should be the stress of the concrete? So substituting from the previous equation that we got, it would be equivalent to 120, that is the value of the stress of the steel, equivalent to 14.39 the stress of the concrete. And if we allow the concrete to reach the steel to reach 120, concrete will reach 8.4 megapascal, and that is exceeding 6 megapascal from the allowable given value, so it will not be acceptable. It is not safe to allow steel reach 120 megapascal. So what will be the safe value then? We have to allow your concrete to reach 6 megapascal, and if you allow the concrete to reach 6 megapascal, what will be the stress of your steel? It would have to be 14.29 times 6, which would be equivalent to 85.74. That is less than 120 megapascal. So therefore the acceptable values will be a stress of concrete equivalent to 6 and the stress of the steel as 85.74. Now if you would ask, sir, why not 120? It's because that the stress of the steel of 120 is its stress in acting alone, but if both of them are acting together, then the concrete will reach 6 megapascal, and while the concrete has reached 6 megapascal, steel will also have reached 85.74 megapascal. A while ago, if we allow the steel to reach 120 megapascal, concrete would have reached 8.4 megapascal and it would have exceeded 6 megapascal. So that's the reason behind it. And substituting in your equilibrium equation, you have the stress of concrete times the area of the steel plus the area of the stress of steel multiplied by the area of the steel is equivalent to your total force P. And therefore, substituting the area of the steel, stress of the steel, and the area of concrete with the stress of concrete, we have 6 times 300 squared minus 6 times 600 plus 85.74 times 6 times 600 is equivalent to P, and you would have a result of P equivalent to 827.06 kilonewtons. Okay, let's have problem number 3. A reinforced concrete column 250 millimeters in diameter is designed to carry axial compressive load of 400 kilonewtons. Using allowable stresses of concrete equivalent to 6 megapascal and that of steel equivalent to 120 megapascal, determine the required area of reinforcing steel. Assume that the elasticity of concrete is 14, and for the steel, the modulus of elasticity is 200 gigapascal. So modulus of elasticity of concrete is 14 and modulus of elasticity of steel is 200 gigapascal. So the figure is this one. You have a circular column, and that column has a load equivalent to 400 kilonewtons, and you want to compute for the steel area. And the solution goes with a given that is stress of steel of concrete equivalent to 6 megapascal, the stress of steel equivalent to 120 megapascal, and the elasticity of concrete as 14, elasticity of steel as 200 gigapascal, with a force equivalent to 400 kilonewtons. The figure is shown below. So applying summation of forces vertical, you know that the force of the concrete plus the force of the steel is 400 kilonewtons, and the deformation of concrete is equivalent to your deformation of the steel. They will both deform together and they are equal. So with substituting your equation for force, which is stress times area, we have the stress of concrete plus the area of the concrete, that is for PC, plus the stress of the steel plus the area of the steel, that is your PS, is equivalent to 400. So therefore, if you're going to use stress of concrete equivalent to 6 and the stress of steel equivalent to 85.74, remember that this was previously compared in problem number 2, because once your concrete has reached 6 megapascal, so with your steel reaching 85.74 megapascal, because they are both deforming together. Okay, so substituting in your main equation, you have the force of the concrete, which is 6, that's the stress, multiplied by the area of the concrete, which is pi times 250 times 250. It's a circular column divided by 4, minus the area of the steel, which is what we're looking for, plus 85.74 times the area of the steel, equivalent to 400,000 newtons, and the area of the steel would be equivalent to 1322.75 millimeters squared. So remember that we won't allow the steel to reach 120 megapascal, because once it reaches 120 megapascal, it will exceed the stress of concrete, which is greater than 6. That was proven in your problem number 2. So I hope with these 3 variations of solving deformations on these first 3 problems, I hope you'll be able to understand the next problems to come. Thank you for listening.